giving this talk. It's really a great pleasure to have you here. So today we have Fabian Gittins from Utrecht University, and he's going to talk about probing dense matter. Giving this talk, it's really a great pleasure to have you. Oh, sorry. And he will be talking about probing dense nuclear matter with gravitational wave astroseismology. Thank you very much. Go ahead.
Yeah, thank you very much for the introduction. Let me start by thanking you for inviting me to talk about my work with you guys remotely. It's nice that we can make this happen despite being so far apart. Let me start by explaining one of the words in my title, which is astroseismology. So I'm just going to play this animation here. Oh, okay. Just click on it. So astroseismology, for those who aren't familiar with the term, is a field of astronomy in which people are interested in oscillation modes of stars. These oscillation modes, you're seeing them, some examples here in this animation, are waves that are sensitive to various features of the star, such as pressure densities, such as its sort of temperature gradients, and so on and so forth. And so it's actually quite a rich problem because essentially each ingredient of physics you add to your modeling, in this case, we're seeing waves as they travel through a star like our sun, tell us something about the seismology spectrum. What is typically done is, and in fact, what is usually done is this technique is applied to systems like our sun, so main sequence stars as well as giant stars. What people do is they generate models of how these waves travel through the star, depending on the physics going on in the interior. And they compare that to electromagnetic data, which measures variability in brightness of the star. And in fact, this technique, astroseismology, we can credit for much of our understanding of the interior physics of our own sun. And in that context, it's known as helioseismology. What I'm going to be talking today about is how we might be able to do astroseismology with gravitational waves on a different source, objects like neutron stars. So here are some bullet points, which are the sort of outline for my talk. And they kind of sort of set the stage for the different sections of this talk. So to begin with, we're going to look a little bit about how gravitational waves actually help us to probe the nuclear physics that goes on inside neutron stars. And I hope that you'll agree with me by the end of the talk that this really is quite a fascinating enterprise. We're also going to learn actually how, when we consider the full dynamical problem of the neutron star binary inspiral, how actually the tidal dynamics give rise to this opportunity to actually do astroseismology of these objects. We're going to see actually how low frequency oscillation modes have the potential to become resonantly excited with the tide and how that might be able to tell us about the neutron star physics. And then very briefly towards the end, I'm going to talk a little bit about some work that I've been involved with on finite temperature simulations of mergers and how we can use these to calibrate our models for astroseismology. So let's start with the first part, gravitational waves probe nuclear physics. So this is the motivating picture for many of us who work on neutron stars or more broadly fall under nuclear astrophysics. What you're seeing here is known as the phase diagram of QCD. QCD stands for quantum chromodynamics, and it's our fundamental quantum field theory for one of the fundamental forces, which is the strong nuclear force. Recall that we obviously have electromagnetism, the weak nuclear force, as well as gravity, and this is the fourth force. Now, while we have a theory for how the strong nuclear interaction is supposed to behave, actually it turns out it's quite difficult for us to calculate within this theory. In particular, and I won't be able to go into too much detail about this, at relatively low densities and temperatures, which are the two axes you see on this graph, and then there's a third axis coming out of the page called asymmetry. At relatively low temperatures and densities, QCD, or moderate temperatures and densities, I should say, QCD is subject to what is known as the sign problem. And this is not unique to QCD. It happens in other areas of physics, and it's really a mathematical problem. Essentially, you're trying to integrate these rapidly oscillating functions. And because of how many oscillations there are, essentially it becomes computationally intractable to solve QCD at these moderate temperatures and densities. And so this sort of blue region, or and maybe even beyond this blue region, really is fair game for us to try to probe outside of theory. When we can't rely on theory, we have to resort to experiment and observations. We've got two, I suppose, parallel tracks trying to constrain the QCD phase diagram. So on this diagram, you should see at relatively low densities, but high temperatures, there's a red arrow, which has the RHIC and the LHC. The LHC is, of course, the Large Hadron Collider. And these Hadron Colliders probe this region, the parameter space.
Hello.
Sorry, I heard a noise just then.
I cannot turn on my camera. I'm sorry.
That's
It's all right. Thanks.
All right.
Go ahead, please.
Okay, I'll continue. So, and maybe actually, this is a good opportunity to say, if people would like to ask questions, I think maybe you could maybe interrupt me because I can't obviously see you all as I'm presenting. Yeah. So let me continue. So that's the low density but high temperature regime. In the complementary regime, we have relatively low temperatures but high densities. And you can see this sort of beige surface coming out of the page here, which says neutron stars and their mergers. And this is the region that I'm particularly interested in. And hopefully you can see that it's complementary. We're looking at two different regimes of the phase diagram. Let me also, while we're on this page, mention at very, very high temperatures and densities, we fortuitously can solve QCD in what is known as a perturbative regime. This is PQCD, as it's referred to, but these are often extremely high densities. Yeah. Is that a question?
No, I'm sorry.
That's okay. I'll continue. So these are really, really high densities at well within what we expect neutron stars to contain. But QCD tells us, perturbative QCD tells us something quite interesting, which is that at these asymptotically high temperatures and densities, we get a new phase of matter. Rather than hadronic matter, which we're used to, we actually get deconfined quarks and gluons. On this diagram, it's referred to as the quark-gluon plasma. And it's actually indeed an open question where the neutron stars, and hopefully you can see the question mark at the bottom of this figure, which indicates this transition from hadronic matter to deconfined quark matter. It's an open question whether neutron stars contain this matter. And I'll talk actually a little bit about one opportunity for that today. And I hope astrocosmology is going to help us build up this phase diagram and our understanding of it. So let me introduce you to neutron stars. So there's a fun cartoon here made by Anna Watts of the University of Amsterdam, which it's a cartoon. It gives you an idea of the different layers of the neutron star. Neutron stars are really quite fascinating objects, and I hope you'll agree with me in the sense that they just have so much physics within them.
I'm sorry, I think I'm getting hacked.
Okay, shall I continue?
Yeah, sure. Sure, continue.
So these are the different. There's lots of very interesting physics within neutron stars. So for one, they're extremely compact objects. So their compactness is only rivaled by black holes, which are other compact objects, kind of almost their cousins, if you will. And for this reason, we really require full general relativity in order to have a complete description of them. As we've already alluded to, they contain some of the densest matter that we know of in the universe, which makes them great test beds for our understanding of dense nuclear matter. And the list can go on. I've written a few of the things that I find interesting. They're extremely rapid rotators. Some of them reach up to hundreds of hertz in terms of their rotation rates. They also host extremely strong magnetic fields. In fact, there's a class of neutron stars referred to as magnetars that have even stronger magnetic fields and have some interesting phenomenon associated with them. They host superfluidity, and they're known to have these solid crusts. And all of these aspects of them actually give rise to their own oscillation modes. So what can we learn about neutron stars from gravitational waves? Well, let me take a step back and just explain a little bit about how the gravitational wave signal of neutron stars differs from that of black holes. So here is a little cartoon that I like to show to illustrate the point. It's ultimately an analogy, but I think it holds relatively useful, and you can get some good intuition from it. I want you to imagine two different compact binary systems, one that has two black holes and the other has neutron stars. And because these are compact binaries, as they orbit one another, they generate, as the two components in the binary orbit one another, they generate gravitational waves through their time-varying quadrupole moment. These gravitational waves take energy and angular momentum away from the system, and so the compact objects in spiral, that's what we mean. They get closer and closer together until they eventually merge. And you can hopefully see that here with the gravitational wave strain. Essentially, what you're seeing is the frequency gradually increases, as well as the amplitude, up until they collide into one another. So if you compare two identical binaries, so the same masses, spins, location with respect to our instrument, the two curves here trace out what their strain will look like. The black hole strain is shown in white, whereas the neutron star one is shown in blue. And hopefully you can see that there is a change in phase between the two. Essentially, what you'll hopefully see is that the neutron star binary inspirals more quickly than black holes. Why is that? Well, the intuition is quite simple. Because neutron stars are fluid bodies, separate to vacuum black holes, as they are in a binary, they develop a tidal field, this sort of almost rugby ball or American football like shape, which is shown in the cartoon. And in changing their shape, this takes energy, and the energy comes from the orbital energy that's available. And so in addition to gravitational waves, there's a tidal energy that goes into changing the shape that shows up. And that's why the systems spiral more quickly. And it's measuring these difference in strains that actually tells us something about the finite size effects going on inside of the neutron star. And this is the feature that we try to exploit in gravitational waves. What we typically do is we make certain assumptions, and we're going to break these assumptions in this talk. We assume that the tide that is raised on the neutron star is a static tide, so we don't worry about any dynamics for now. We make the following two assumptions, which I think are kind of useful to spell out. We assume that the two component bodies, the two compact objects, are well separated. So I introduced this small parameter epsilon. This is almost always true throughout the inspiral, except for the final few orbits when the two stars are very, very close together and then eventually merge. In this regime, ultimately, we have to contend with nonlinear general relativity. And so what people do is they put these objects on a computer and they simulate the final few orders. That's what's meant by numerical relativity simulations. This is kind of inevitable. The second assumption, which again we're going to want to relax in this talk, is that we assume that the star's orbital frequency, or the orbital frequency of the binary more accurately, is slow. And this is certainly true when they're far apart from one another. So I've introduced this small parameter lambda, and that's built out of this phi dot, which is the orbital frequency of the binary, and this small omega alpha, which is a mode frequency that we'll return to later. And we've used the static tide to exploit the two neutron star binaries that we've seen to date. These are GW17817 and GW190425. In case you're not familiar, this naming convention comes from the date of detection. So the first two digits correspond to the year. So GW17817 was seen in 2017. It was seen in August, which are the third and fourth digits, and it was seen on the 17th of August. So 17 at 17, you can see on the left some results from that particular event.
Proud of you.
Sorry, was that? Shall I continue?
Go ahead. I guess there was a noise or something.
Okay. So what's on the left shows you some of the results we get from 17 at 17. So what you can see here is a posterior probability distribution. This is essentially a data product we get by comparing models of the gravitational wave signal with the data. And there's a particular parameter we're estimating here, which is this lambda tilde parameter. We don't need to go into detail on this, but essentially it's a mass weighted average of the tide that is raised on each star in the system. And what's significant about this is that actually it's kind of got peaked behavior, which indicates kind of more favorable values of this lambda tilde parameter. And so this essentially constitutes a reasonably good measurement of this parameter. It's not perfect by any stretch of the imagination, but it's quite nice to see this as proof of principle. And the hope is with many detections, you get better constraints on these kind of quantities. On the right, I'm showing you is the results for 1904-25. This was a significantly quieter event. It had lower signal to noise ratio, which meant that we were able to get weaker constraints on the source parameters. And actually, you can see if you ignore the blue curve, which is just the results from 17 at 17, you can see that actually we learned very little about lambda tilde. It was a very weak measurement, and actually you could even argue that it's consistent with zero. So you could argue that from the gravitational wave data alone, we can't be certain that what we saw were neutron stars rather than black holes. But the hope is we can do better in the future with more detections. So let me move on to my second point in the talk, which is about sorry, I'm finding some of these
Yeah, we see
it's quite distracting. Yeah.
I'm trying to catch up to remove them, but they're faster than us.
Okay.
Go ahead.
Okay, I'll continue. So let me move on to the second point, which is how we're going to connect all this to astroseismology. And I think this is hopefully going to be new and interesting. So we saw this a few slides ago. This was essentially the state of the art a number of years ago. And in particular, what we want to do is we want to relax this constraint at the bottom. And this makes the problem obviously harder because now it becomes a dynamical problem. We have to worry about time dependence. But we're going to allow the orbital frequency to increase appreciably, which is obviously going to happen anyway in an spiral. In fact, let me go to my next slide. This here is actually a spectrogram from 17 at 17. This was when they removed that enormous glitch that maybe some of you are familiar with. But this is essentially tracks of the gravitational wave. And it's probably most clearly seen in the middle panel. I should explain the three different panels correspond to the gravitational wave as measured in the three instruments that existed at the time. They're the two LIGO instruments, LIGO Hanford and LIGO Livingston. And the third detector is, of course, the Italian Virgo instrument. And it's most clearly seen in LIGO Livingston, which was the most sensitive instrument at the time, and it still is the most sensitive instrument we have. And you can hopefully see this beautiful chirp as you go to, from low time to high time, or late time even. So, and this is the gravitational wave shown in this, and the color, the amplitude tells you something about the amplitude of the radiation. And actually, because the instruments aren't super sensitive at very, very high frequencies, essentially we don't see it going much beyond a few hundred hertz. But in principle, this system would have inspiraled and merged at about maybe 2000 hertz, something like that. And so actually from this picture, you can already see that the approximation that the tide is static, i.e. the orbital frequency is slow, is clearly going to break down at a certain point. And this small omega alpha is a frequency that corresponds to the hydrodynamical frequency of the star. It's a mode frequency. And there's one mode that we can estimate quite easily, which is the fundamental F mode. And that can be estimated quite simply by looking at the average density of the star. So m over r cubed gives you density. This is just the square root of that. And how do you build a frequency? Well, you bring in the Newton's constant g here. And by putting in typical neutron star values, so 1.4 solar mass, 10 kilometer radius, you immediately get an F mode frequency about 2.2 kilohertz. And this is broadly correct when you do the full calculation. And actually, there are many other frequencies even below the F mode. So actually, while this is a kind of almost an upper limit in terms of when we expect the static approximation to break down, in principle, it could break down much, much earlier than this. So lambda eventually becomes not a small parameter at all. Oh, next slide. So let me introduce to you some of the modes. I've got some animations here, but I guess I can only play one at a time. We typically think about these modes using a spherical harmonic basis. And so I'm just showing you some animations here to kind of catch your eye. These spherical harmonics tell you for a specific radius in the star how the mode moves. And of course, the frequency at which this moves corresponds to the frequency of the mode. And there's also obviously a radial dependence. These are some of the oscillation modes that we typically meet and are probably important for gravitational waves. The first one is the fundamental F mode. And this is the mode that, in principle, you can imagine building a very, very simple stellar model, one that's purely Newtonian, incompressible fluid. And in fact, this is the first mode that was discovered by Lord Kelvin, also known as by his other name, William Thomson, back in the 19th century. And this is a mode that scales with the average density, and it dominates a lot of the dynamics when it gets excited. Then you can imagine you want to do better than Lord Kelvin. You give your star an equation of state, so a pressure versus density relationship, and that gives rise to a finite speed of sound. And so you get what are called pressure waves, or P modes. I like to think about these as overtones of the F mode because they have higher frequencies than the F mode, but they more or less arise from very similar physics. They're both pressure waves. You could also want to go beyond a simple barotropic equation state and include things like thermal or gradients, or even composition gradients, the latter being more important for neutron stars. Essentially, the idea is you can have like a fluid element in your neutron star, and suppose you move it to a different position, it suddenly finds itself in a region of the star. It'll pressure equilibrate quickly, and because the nuclear reactions around it aren't fast enough to equilibrate that fluid element with its new surroundings, it experiences a buoyancy force, and so it goes back and forth, back and forth. And these are, of course, the G modes. You could also give your star some rotation. You then give rise to what are known as the inertial modes, along with one particular famous member of this inertial mode family known as the R mode. You could give your star phase transitions, so discontinuities in the density, or you could even give the star a phase transition from fluid to an elastic crust, and this will give rise to what are known as the interfacial I modes. And then there's many more. It really is a very rich problem, the seismology of neutron stars. There's gravitational wave W modes, shear S modes due to the shear modulus of the crust, as well as alpha modes that arise due to magnetic fields. So allow me to maybe get a little bit mathematical here, and I won't do too much of this in this talk, but I think it's quite instructive to understand how we actually calculate the dynamical tide. So there's a really nice idea that goes back to Chandrasekhar back in the 1960s. Chandra noticed that if you imagine that you just focus on Newtonian gravity for simplification, and you just consider a perfect fluid star, so there's no dissipation in the problem at all, there's no gravitational waves, there's no shear or bulk viscosity, there's nothing like that. Then what Chandra noticed was that the modes of the star are form what is known as a complete basis. Essentially, this equation here on the right, there's two equations at the top. The one on the right is the equation that describes modes. It's a nonlinear eigenvalue equation. And Chandra noticed that the solutions, at least the eigenvalues, are real. And so therefore, this problem is what is known as Hermitian. And that means that you're permitted to build a vector basis out of its solutions. I should probably explain the xi here, this Greek letter xi, is what's called the Lagrangian displacement vector. What it describes is if I kick a star and it starts oscillating, xi tells me essentially where the fluid element moves to during a perturbation, right? And so essentially what you can imagine what we really care about is we care about the tidally deformed neutron star. And xi basically says when the star is put into a tidal field, where do the fluid elements move as a function of time and position? And so suppose we follow Chandra's argument through, we can expand any generic vector using the oscillation modes. We can write an equation like the left one, the one on the left at the top. And this here is a sum over all the different oscillation modes. Essentially, the statement is you can always build any displacement, in this case, the tidal displacement, out of an infinite sum over all the oscillation modes. And once you do that, actually, you take care completely of the spatial dependence of your problem, and you get an equation like what's shown on the bottom. This is, there's no prizes for pointing out exactly what this is. This is obviously a forced harmonic oscillator, and it's no surprise we've ended up here because this is exactly how we've set up the problem. We've described our star as a collection of harmonic oscillators, and we put it into a tidal environment. What you have essentially is a one-dimensional problem at this point. You have to solve this second-order differential equation in time. On the right-hand side, you can see the forcing term, and that is, of course, due to the orbital frequency of the binary, among other things. I'm including, just for completeness, a term on the right-hand side, this calligraphic E. You don't need to worry about this. This is a mode normalization, because essentially whenever you calculate oscillation modes, the unforced problem, you've always got a free amplitude, and so you must normalize. But this isn't something you need to worry about. I just put it there for completeness. So let me move on. So we've got an equation. So let's have a look at the solutions to our equation. So you can imagine a very simplistic case, and this won't describe our full problem, because of course we're interested in spiraling neutron stars. You could take an equilibrium orbit, and that's to say that this phi dot is constant. Essentially, this is the statement that the two stars are always separated by the same distance, and that the star is in sort of Keplerian orbit. When I make this particular assumption, I can solve the second-order differential equation exactly. I get a solution like this. This says what happens to the mode as a function of time. And from this, I can make plots, which are shown on the bottom. And the plots basically describe how significant the different modes are relative to the F mode. So that's why none of them reach 1, and they're all fractions of 1. They're all smaller than 1. There's a few takeaways from these plots. One is the F mode is the dominant contribution to the dynamical tide. In fact, you can see at about 1.2 on the x-axis. This is a dimensionless version of the orbital frequency. At about 1.2, all of them become very insignificant because this is when the F mode is resonant in this sort of toy problem. The second takeaway is if you look at the two panels on the right, the numbers that you're seeing, this gamma 1 is the so-called adiabatic index. It basically describes how non-barotropic your fluid is. So when it's appreciably different to 1, essentially you've got something like chemical composition in your star. And of course, as we mentioned earlier, when we looked at very briefly at the G modes, whenever you've got composition gradients, you give rise to these buoyancy waves called G modes. And what you can see is depending on the value of this gamma 1, the G modes can become resonant, and they can be actually very significant. So suppose gamma 1 is very different from 2, is a lot bigger than 2. You get the right panel, and you can see that the first overtone of the G mode, this sort of yellowy green curve, if you can see it, gets very, very big at resonance. And so there's an opportunity here, which is to look for resonantly excited oscillation modes. So that's one option. I won't spend long on this slide here. This is just interesting for people who, for those who are interested in the formal aspects of the problem. Of course, for consistency, you could imagine that you want to reclaim your static limit. This might seem a little bit pointless because we saw earlier there's just this one parameter, the lambda parameter, which describes the static tide. And so you could argue, I've made the problem very confusing. I've recovered the static limit, but now I've got an infinite sum. So Q alpha here is now time independent. This is obviously not how you want to actually calculate the problem. You really want to just focus on the tidal Love number, the capital lambda, the tidal deformability. But what's quite interesting, at least for people like me who care about modes, is even in the static case, you still have oscillation modes show up. And furthermore, suppose you are interested in things like G modes, even if your equation state has non-barotropic aspects, these don't show up in the static problem formally. You know, if I've got a non-barotropic fluid, it doesn't care at all about weak interactions. However, here in the static problem, where I haven't made those kind of assumptions from the outset, I can actually sum up all the oscillation modes. That's what's been done in this table here. And I can recover the tidal deformability to very high accuracy. And this is kind of interesting because essentially it shows that the G modes still exist in the problem, even in the static problem. But even though the problem is static and therefore you don't need to worry about non-barotropic aspects. So this is kind of interesting to me. You know, maybe it's only interesting from a formal aspect, and I don't propose that this is a way of actually doing astroseismology, measuring these oscillation modes. But for me, it's kind of interesting to see how G modes still show up in the problem. So basically, as I kind of conclude this particular section, one of the key takeaways is that the F mode is the dominant contribution to the tidal response of the star. There have been a number of approaches developing gravitational waveform models for the F mode dynamical tide. I list some of the directions here. There's effective one body, Newtonian, and phenomenological approaches. Here I include on the right a plot from Jan Steinhoff's 2016 paper, which shows you essentially how different the tidal response can be when you go to the dynamical tide. So what's shown here in dashed lines, these dashed horizontal lines, is the result if you assume the tide is static. These KLs are what are called the tidal Love numbers. And what's shown in solid lines are essentially these effective frequency-dependent tidal Love numbers. And what you can see is that as you get to higher frequencies, which is what you're doing is you're going along the axis to the right, these numbers can be appreciably different. And so this is something you obviously do need to worry about. Right, let me move on to my next point, which is about what the opportunities are afforded to us by low frequency oscillation modes. So I won't be able to go into detail onto all of these different oscillation modes, but I hope they can provide a relatively high level summary about some of the work that I've been involved with regards to them. So this obviously isn't exhaustive, but in particular, I've been focusing on G, R, and I modes. And the reasons we expect them to become resonantly excited, just to maybe rehash some of the earlier slides and put a more formal flavor on it, is this equation I showed you earlier, which is for the equilibrium orbit. You can see that there is a particular value at which the denominator becomes, it sort of blows up. It goes to zero, and therefore the whole thing gets far too large. This is the resonant condition, and it essentially corresponds to this equation on the right-hand side of the slides here. Essentially, what you see on the left is the tidal frequency. This M here is this quantum number, which describes the spherical harmonics. And the phi dot is the orbital frequency. It's the time derivative of the orbital phase. And when this matches the frequency of a given oscillation mode, omega alpha, this term gets very, very large. And the intuition is quite simple what happens here. Essentially, all of a sudden, the mode grows in amplitude, and therefore the energy gets pumped into the oscillation mode. And this can come from the energy budgets that are available to the mode. Typically, this is at least under certain assumptions, this is typically the orbital energy that exists. And so as energy gets transferred suddenly from the orbit into the mode, you can imagine that the binary suddenly advances. It gets closer to merger. And so you can parameterize this in terms of a delta phi, a sudden change in orbital phase. And this is the number we'll be using for some of these plots that I'll show you now. So let's focus on G modes first. So I like to think about this problem in terms of the thermodynamics. And what you're seeing here is the first law under different assumptions about your nuclear matter. So the first equation corresponds to a very simple idealized situation of purely hadronic matter with neutrons, protons, and electrons, and they're in equilibrium, charge equilibrium, as well as the reactions on equilibrium, and you get a one-parameter equation of state. So this epsilon here is the energy density of your fluid, and the n sub b is the number density of baryons. Super duper simple. This is essentially the argument that would lead you to calculating lambda tidal formability. Now, I think we want, and at least I think I speak for other people, that we'd like to probe other aspects of the nuclear matter. And something that I think is quite interesting are reactions and additional non-barotropic aspects. And so imagine you take into account weak nuclear interactions. So that's this mu delta quantity. So this is the chemical, it's a quantity that describes the chemical equilibrium between neutrons, protons, and electrons due to the weak interactions. Suppose that this is non-zero, and sorry, this Y sub E is the electron fraction of your fluid. Suppose that this is non-zero, then you've got a non-barotropic equation of state. And this is what we expect for neutron stars. In fact, actually, as I show on the right, these are some curves taken out of a paper, which tell you essentially what these are BSK models, which are quite nice analytic equations of state, which are nice to use. And they're obviously not all the equations of state that you can use, but I think they illustrate the point that is, for these realistic models, there's a great amount of uncertainty in terms of what we know about nuclear matter in general, and in particular these kind of reaction rates. But what is interesting is these two different models are different to zero throughout the star in general. So in general, we expect the nuclear matter to be non-barotropic. This gamma 1 we met earlier is called the adiabatic index, and that describes this. And then on the x-axis, you see the number density of baryons. So this is a figure from one of the papers that I was involved with. What you're seeing, and we'll see a couple of these figures throughout this the rest of the talk, is you're seeing on the y-axis this change in orbital phase at resonance, and on the x-axis you're seeing frequency of the oscillation mode. What the dots correspond to different equations of state and oscillation modes from those different equations of state, and the lines of the curves are estimates for the sensitivity of ground-based gravitational wave instruments. The top curve is A+, that's LIGO A+, and that's the planned upgrade to LIGO, which should be built, if things go to plan, in 2028 for the O5 observing run. The other two curves are Einstein Telescope above and Cosmic Explorer below, our third generation gravitational wave observatories, which are planned for the future. And the story, you might argue, is a little bit pessimistic. I wouldn't disagree with you, but there are perhaps some reasons to be cautiously optimistic. So you can see here, depending on the equation of state that you believe describes the nuclear matter the best and the reactions the best, actually some of these phase shifts can actually be appreciable. And recall, these are just estimates for the sensitivity of these instruments. In principle, they could be better. There could be other techniques for extracting these resonances. But the key point is, if you look at, say, the BSK22 models, These are in principle in reach of third generation instruments and possibly even A+. And the story gets pessimistic for some of the other ones that have weaker barotropic aspects. Let me just move on to the I modes. So the I modes arise whenever there is a phase transition in the star. So here's a nice figure from David Tsang's paper where he pointed out that these kind of interface modes that sit at the base of the crust can give rise to resonant shattering flares. I'm not going to focus on that here today, but this is one possible manifestation of the I modes, as they can exist at this crust core interface. The type that I'm particularly interested in is one, it's hypothesized, it may or may not exist, and it would exist if there is deconfined quark matter in your star, and that there is a first order phase transition between deconfined quark matter and hadronic matter. So these are the equations of state that we used in this particular paper. What you can see is mass radius and tidal formability mass curves for these different equations of state. Not all of these ones, actually, by the way, have phase transitions. Some of them do, some of them don't. We kind of want to look across all of them in our analysis and see which ones actually give rise to interface modes. You can tell the model has a phase transition if you can see a sharp kink in kind of either of these figures. Maybe let's look at the left one for now. And you can see essentially that there's some variability where these kinks might arise. We were fairly agnostic in this study, so we didn't fix any observational constraints on the matter models we looked at. And what's kind of important is you can see some of these curves have kinks above and below 1 solar mass. Now, why is 1 solar mass significant? Well, 1 solar mass, or maybe more like 1.2 solar masses, is basically the minimum mass we expect a neutron star to be birthed with from a supernova. And so if we believe this, this is robust and true, and there aren't any neutron stars below 1 solar mass, then you can see that some of these kinks here would never be measured if you just measured mass, radius, and tidal formability of neutron stars, which are the parameters that we tend to measure anyway. And this is what's known as the masquerade problem. Essentially, the idea is that based on your measurements of these kind of quantities, you would not be able to distinguish between a curve that's from hadronic matter or quark matter, because essentially you're not probing that particular transition. So this is kind of an interesting problem. And I wonder whether the dynamical tide might help us get to the bottom of it. So these are some equations which come from a very simple analytical calculation of an incompressible neutron star with 1 first order phase transition. The key quantities in this model are epsilon, so that's this relative jump in energy density at the phase transition, and r sub I, which is the radius at which the interface occurs in your star. And you can see for typical neutron star values, you get frequencies that are about maybe 700 hertz. The second quantity that I'm showing you here on the slide, this Q sub L, is called the tidal overlap. Essentially, the larger this number is, the more efficiently the mode couples to the tide. And so, for example, for F modes, this number is very large. For G modes, this number is typically 10 to the minus 4, 10 to the minus 5. We also did the full calculation in general relativity, and our results are summarized in this particular figure. So this is the same as before. This is a change in orbital phase versus the frequency of the oscillation mode. The sensitivity curves you see here are LIGO Livingston at 17 at 17, LIGO A plus again, Cosmic Explorer again, and Einstein Telescope again. And the dots correspond to different equations of state, which therefore have different properties for this phase transition. In fact, the color bar tells you about the relative change in energy density at the phase transition. And I want to draw your attention to one particular oscillation mode that's shown here, 964. If you allow me, I'll go back 2 slides. So 964. So 964 is, and apologies for anyone who has any form of color blindness, maybe I'll use my cursor to help me. 964 is this equation state model here. It's in brown. And in case you can't find it, it's this equation of state here. And I'm tracing over the phase transition. And what you'll notice is that the phase transition here manifests at about 0.5 solar masses, a radius of just over 12 kilometers. This, in principle, if this were the true equation state, which I'm not claiming it is, this would fall afoul of the masquerade problem. However, if I go back to my figure here, it has a clearly identifiable interface mode. And in fact, this interface mode has quite a large dephasing associated with it. And it could have been even large enough to see at 17 like signal. Even supposing that we look at the other oscillation modes here that from different equation state models, the takeaway from this plot is essentially the interface mode is significant, and it's potentially within reach now with our current instruments, and quite likely even with third generation. So I think this is quite nice. Let me just check. Am I doing okay for time? Do you want me to wrap up anytime soon, or?
You're doing just fine, no worries.
Okay, cool. I've only got about 3 or 4 more slides. So let me move on to the final part of the talk, which is a little bit tangential, but I kind of wanted to share this because I find this quite interesting. So we're going to think about simulations now. Now this is still related because, and actually this figure here summarizes essentially how we use simulations. So simulations are vital for the final few orbits of not just neutron star binaries, but also black hole binaries. And that's because we enter a nonlinear regime of Einstein's general relativity. And so we are forced to work with computational calculations. And this is obviously fine. And we've been doing this stuff. And certainly the black hole enterprise is extremely mature at this point. And we're doing these simulations for neutron stars. And what is typically done is there's 3 regimes of a neutron star of a neutron star binary. There's the in-spiral, there's the merger in the middle, and then there's the post-merger. This is sometimes called the ring down in black hole contexts. And we have analytical models of the in-spiral, but we don't have analytical models for the merger and post-merger for reasons I've just described. So what we typically do is we match in-spiral models to merger simulations. And so simulations are really a very, very vital part of our effort to be able to detect gravitational waves from these systems, as well as perform parameter estimation on them. I think it's sensible to include temperature in these simulations because, of course, we expect them to be warm. There's obviously big fluid bodies that are smashing into each other at relativistic velocities. So we want to include finite temperature into our modeling. And they get quite hot. So what you're seeing here are at merger and 5 milliseconds after merger is a simulation from a collaborator of mine, Peter Hammond. And you can see, certainly in the left half of these 2 panels, the temperatures that these simulations reach, and the color bar that you should be looking at is on the left, the temperature in mega electron volts. And you can see that actually temperatures can be very, very high. They can even exceed 60 mega electron volts, which is extremely warm, but maybe that's sensible. These are obviously very kind of cataclysmic events, dare I say. However, it seems like there are a number of pathologies which are known by the community in these temperature simulations. So what I'm showing you is a neutron star, so an isolated neutron star with a finite temperature equation state that is placed on a numerical relativity grid and simulated. There's no merger happening. We've just got an isolated star. And what ends up happening, because the discretization of the numerical relativity grid is essentially shocks appear. So you can see these shocks because this is where the temperature gets largest. And the different panels correspond to different resolutions, so low, medium, and high resolution. So maybe let's have a look at the right one the most. And you can see after just simulating these systems for a very short amount of time, milliseconds and maybe even fractions of milliseconds, I can't quite recall, you can see that the temperatures already reach well over 1 megaelectron volt and sometimes even 6 megaelectron volts. This is something like 5 orders of magnitude higher than we expect an isolated neutron star to be. They're typically 1 or 0.1 kiloelectron volts. So this is a well-known pathology, but I worry that it's causing an issue. And in fact, we looked at this problem. We asked ourselves the question, okay, let's take a merger simulation and let's look at the final few orbits before they actually merge. And let's calculate the tidal deformability as well as the oscillation modes that that neutron star has based on that temperature distribution. The results are the dashed lines, which I don't know if they're super duper visible. Maybe I'll point them out here. So the tidal deformability of the star in the merger simulation was about 530 to 540. For reference, you can see that at very low temperatures, say the cold neutron star, which is what you'd expect, even 5 orbits before merger, because they haven't yet collided. A cold neutron star should have a tidal deformability of less than 475. So there's a big difference there. And a similar story you can see for the oscillation modes. And so it seems likely that these temperature effects may actually filter into any sort of parameter estimation that we may want to do with tides and dynamical tides in the future. There's obviously more work to kind of pick up on there, but this is kind of this paper was more of a proof of a principle than anything else. Let me now wrap up. I can see I've got about 8 minutes left or so. So hopefully there'll be time for some questions. There's lots of opportunities with gravitational waves and our ability to probe the QCD phase diagram. And we will do this by measuring tidal deformations in in neutron star binaries. And I hope that I've got you guys maybe excited or at the very least interested in our ability to be able to do astroseismology with gravitational waves. And these oscillation modes really can grant us access to some of the rich physics going on inside neutron stars. For me, what's particularly exciting is the potential to be able to go beyond the barotropic equation of state. There's some challenges ahead. Some of the ideas that we rely on for calculating the dynamical tide essentially rely on arguments that are completely embedded in Newtonian gravity. So Chandrasekhar's idea doesn't apply when there's dissipation in the problem. And so in general relativity, all non-axisymmetric motion gives rise to gravitational waves. That's inherently dissipative and ruins a mode sum. So there's some interesting work going on in that direction. More needs to be done. We really do need to develop gravitational waveform models of these features to robustly perform parameter estimation, and maybe even before then, assess the detectability of these modes. And then finally, related to my final few slides, I think, and this is obviously a very big point, is we would like to try to address systematics and finite temperature simulations. Thank you very much for listening. I'll hand it over to our chair.
Thank you very much. Thanks a lot. It was a good, very nice talk. So, are there any questions that we can have? A few questions, definitely. I actually kind of have one. Maybe I probably missed. So, how early before, let's say, how should we start? When should we start observing these merger events to actually see signatures of different oscillations, for example? I believe they will be like at the very end. I mean, usually they are only detected with gravitational wave observatories anyway towards the end, I guess, because of the frequency dependence of the detectors, of course. But how early, or what is the earliest we can see that because of, let's say, I don't know, some one of the modes we would be seeing some difference in the signal apart from what we normally expect from.
Yeah, yeah. Is your question about what frequencies these show up, or is it more when will our instruments become sensitive enough for it to be a problem?
Actually, kind of both, I guess.
Yeah.
Like, for example, if there is a, let's say, an R mode oscillation in a neutron star by itself sitting somewhere at the moment, we cannot see that with X-ray telescopes, right? That's fine. So I was wondering, like, for how long would we be able to see that if we had an ideal, let's say, gravitational wave detector? At least we can maybe think about that one. So when it will become significant enough, these oscillations would become significant enough to actually create some deviations from what you would expect to just have from these two otherwise solid objects rotating around each other.
Yeah, no, it's a very good question. I don't have an answer because I think this is something that needs to be done really to assess essentially systematics by ignoring this stuff. The reason this problem hasn't been pursued, kind of twofold. One is one is quite simple. We've never developed the models for these things. This is an active area study, and this is something we're working on. The second one is it was assumed that these phase shifts, if I show you, maybe I'll go a slide further slides down. These kind of phase shifts here, these were certainly beyond the reach of the initial plans for the LIGO instruments. You know, many people were thinking about kind of seismology decades ago, but they actually just discarded it because they thought these phase shifts were too small. So it's kind of been resurrected as we've seen just how sensitive some of the instruments can become. You know, LIGO A plus here is, I think, well beyond people's wildest dreams. But yeah, it's a very good question. I think we need to understand this. And systematics in general in gravitational wave astronomy are becoming a huge issue. In terms of frequencies, maybe this slide gives you an idea. It depends entirely on the mode, and there's many, many things that we need to do in order to get a more complete understanding of the seismology problem. You can see G modes here are typically order hundreds hertz. These interface modes, which I think are admittedly more speculative because, you know, is there a first order phase transition to deconfined quark matter? That's an open question. They can be 700 hertz to 1000 hertz. So it kind of can happen. But I think in terms of what I'm personally working towards is understanding this kind of 50 to 300 hertz range. I think that's a good range to start looking at.
I see. All right. There's one more question coming from the chat. I don't know, maybe I can just read it quickly. Given the challenges in modeling and extracting oscillation modes, do you think machine learning could help identify subtle mode signatures in noisy gravitational wave data?
Yeah, great question. Well, machine learning is proving to be really actually quite useful in gravitational wave astronomy at the moment. I'm in a research group where many people are thinking about how to use machine learning, particularly for like non-stationary noise, so more detector characterization, stuff like that. I think it's an interesting idea. I'm not a machine learning person myself, so yeah, why not give it a go and see if you can. My suspicion would be, given, you know, as the question admittedly mentions, these are subtle signatures. Subtle signatures are kind of notoriously difficult to tease out without precise models. In fact, you know, the whole of gravitational wave astronomy has relied on, and this is what makes kind of our field, the gravitational wave field, quite remarkable, is because we've got such good models, is that we can therefore tease out signals that are 1 to 2 orders of magnitude buried into detector noise. You know, the detector noise is something like, you know, 2 orders of magnitude larger than the signals that we have. And it's because of really good models that we can actually tease out that information. And I suspect the issue will be the same in mode signatures. I hope I answered the question, but it's a problem worth exploring.
All right, thank you very much. There's one more question from Kai. Kai, I have to first understand how I can actually allow you to.
You've been silenced.
Yeah.
Okay, I
Go
hope this
ahead.
works.
Sorry.
Okay, thanks for the very nice talk first. I have one question. So these I modes, at what point would they become sizable? Say, how many cycles before merger? And is this still in a regime where everything is nice and analytic? And
Yeah, sorry. So there were two. Yeah, the question when that happened very late, and in fact, this was a question that the referee asked us to understand, which was so the frequencies here are 1,000 hertz. The merger for an equal mass 1.4 solar mass binary is about 2,000 hertz, but obviously the frequency evolution at that point, you're into the final few orbits or so. We found that all the modes we considered became resident before merger. That's obviously an important consistency check, but it would be very, very late. And I think that's going to make these hard to find. So, these are a couple of orders of magnitude larger phase shifts than the G modes as a comparison, but the trade-off is they're very late in the inspiral. Yeah, I've kind of, pun intended, oscillated in terms of my excitement about these interface modes because they are so late. I think we won't know, kind of anticipating kind of a follow-up question, we won't know how detectable they are without proper models. That's really what we're lacking at this point, because these curves are kind of just comparisons based on strain sensitivity of these instruments, but they're not super robust. Was there a second question within your question that I've
So
missed?
yeah, I mean, if it's still possible to do this analytically, if they stretch it up to that point, at what order in a post-Newtonian expansion would they come in?
So, well, this is an entirely Newtonian argument. In terms of the post-Newtonian expansion, certainly when people talk about the tide being a 5pn correction, what they mean is that it has frequency dependence that mimics a 5pn correction. I don't know exactly the frequency dependence they enter in. There's some really simple phenomenological models that just have a step function in your frequency transformed gravitational wave strain. But this is a Newtonian effect. I think that's kind of important to explain. I'm sorry, I don't think that was a good answer to your question. I guess the honest answer is I don't know.
Okay. I guess, I mean, if you really then need a template to search for, you need to do post-Newtonian. You cannot do everything just Newtonian. I mean, the mode itself is Newtonian, but the anti-gravitational wave signal then will be at some probably very much higher order in the post-Newtonian expansion. And yeah, I mean, if that would be feasible, if one could stretch the expansion, maybe there's a chance to find them. Because as soon as you need to do simulations, I guess then things get messy, and then it depends on initial conditions and all kinds of things. It will be very hard to search for them.
100%. And I think, gravitational wave form people, I think, if there are in the audience, you'll be totally unsatisfied with what I presented here because there's so much more work to be done. This is what I presented here is the astrophysics in terms of the neutron star response, but the actual calculation of how does it affect the orbit there's much more to do there. 100%.
Okay, thanks so much.
Thank you very much, Fabian. One more time, thanks a lot, Kai, for the question. And so thank you very much one more time for this very nice talk, and maybe see you next time in person somewhere.
Yeah, that'd be lovely. That'd be lovely. Yeah, do come up to me if you see me at a conference and say hi.
Sure. Yeah, why not? Thanks. Bye.
Thank you, Fabian.
Oh, thanks everyone. Bye-bye.